I'm deaf, so I can't hear. Okay.
Okay. I'd like to introduce David. David's going to talk about his work with teaching linear algebra. Thanks, David.
Okay, thank you very much. Thanks for the opportunity to talk. Can you actually hear me? I should warn you, I'm almost completely deaf, so I can just hear my voice. Okay. Okay, so I want to talk about incorporating principles with a view to enhancing student learning and understanding, right? So, of course, it's an axiom in the practice of mathematics that proof is sacrosanct. But you can ask whether you can ask about the role of proof in the pedagogy of mathematics. And there was a warning by Hannah Neumann from 1971. She wrote, "One can teach it, mathematics and insight, by informal methods, but proofs are useless or worse." And the context of what she was saying was she was explaining in a class why the column and the row rank of a matrix are the same. Okay, and she was quite disappointed, almost shocked, that one of her better students reacted, "But then you proved it, and that spoilt it all." Okay, so of course you can't spoil the theorem by proving it, but you can spoil the perception of the mathematics or the attitudes. As it relates to in the plenary talk we heard about perceptions and attitudes. So there's this issue. And Poincaré wrote in 1914, "It is by logic that we prove, but by intuition that we discover." This was taken up by Francis Su in a nice paper in 2010, where he writes, "The principal aim of teaching is to nurture the mathematical yawp and transform it into poetry." And what is a mathematical yawp? Well, it's an expression of surprise, delight, a discovery of the beauty of some mathematical idea or argument. Okay, and he quotes the Dead Poets Society, where John Keating says, "I sound my barbaric yawp over the rooftops of the world." And he's quoting from a poem of Walt Whitman. Okay, and Francis Su describes these things as fun facts and aha moments, right? Let's sort of elevate this idea of intuition into something memorable and engaging. Okay, so what I want to do is take this idea of the mathematical yawp, and weave it into the fabric of teaching through certain principles that enable the student to sort of stand back and try and see connections. Okay, so I'll talk about three principles. The linear algebra principle, which says move in straight lines wherever you can, which makes sense because of the adjective linear. The plateau principle, which says look for and be prepared to use a variety of plateaus as starting points for an investigation. And of course, we use the plateau principle all the time when we do research mathematics, when we quote other people's theorems or results. Right? But it's perhaps not as obvious. It's used in mathematical teaching often implicitly when you rely on results or techniques or theorems without actually saying, right? And what I would like to sort of emphasize is make that explicit if you can, because then students will appreciate it and they'll be able to start to see the wood for the trees. And the third principle, the conjugation principle, says to do something difficult, change your position so that things get easier and then return. Okay, so I want to turn that into symbols. And in the spirit of Francis Su's comment about poetry, and in the spirit of the plenary this morning where we heard some verse, we've got a poem to explain obstacle avoidance. If you wish to make a cake, then find an oven in which it may bake. But if, on the other hand, you prefer ice cream, then the refrigerator may be the answer to your dream. Second verse. The difference between the foolish and wise is sometimes the ability to compromise. For if the feelings of others you need to placate, the solution may be simply to conjugate. So what's all that about? Well, here's somebody going for a job unsuccessfully. Right? They didn't succeed in persuading the interviewer. However, using the conjugation principle, by changing the appearance, they were able to get the job. So can you see the difference? Completely different outcome, but the only difference in leading up to that is the insertion and deletion of a tie. And we can express this symbolically. Let Z be representing something difficult. X is changing your position or environment or appearance, whatever, to make something easy. That's called Y. And then you can undo X later, no problem. Okay. So what we're doing really is a form of obstacle avoidance. If you want to get from A to B and there's an obstacle in the way, you step sideways with X so that you can use the linear algebra principle to move in a straight line Y, and then you undo X to arrive at your destination. Okay. So the Z equals X, Y, X inverse avoids the obstacle. There's lots of examples, right? So getting a job, we've just explained. Baking a cake is quite interesting. You make a cake on a bench, but it doesn't cook. It's difficult to cook on the bench. So you put it in the oven. You turn the oven on very easy and you wait a little while. Then you undo X when it's cooked and put it back on the bench. You have to be careful. When you take it, it's hot, right? So it's difficult to undo X. You first put oven mitts on. You then undo X, and then you take the oven mitts off. So we're using the conjugation principle in order to undo X. We've got an intertwined conjugates. Being transported somewhere, if you want to catch a train between stations, you on the platform, when the train arrives, you step onto the train, that's X. It's very easy to stay on the train while it transports you to the station. Then you undo X and you arrive at your destination. Passing exams, we've all had the experienced students cram their heads full of information in order to make it easy, or at least possible, to pass an exam. And then afterwards, they allow their heads to become empty vessels again. Diagonalizing a matrix, if M's a messy matrix and P is a matrix of eigenvectors, then you have the equation MP equals PD, where D is diagonal. And if P is invertible, then you get the equation M equals PD P inverse, which is an instance of the conjugation principle. Okay. Now, what I'd like to talk about is conjugations and combination. I already hinted at one example with baking a cake, but the most common example is the commutator, call it C, the expression X, Y, X inverse, Y inverse, which is two intertwined conjugates. And it gets its name because it's a measure of how far X and Y are from commuting. Okay, truck drivers use commutators to make a living. Right, so here's a truckie transporting goods from shed 1 to shed 2. Say takes goods labelled A from shed 1 to shed 2. Right, and then on the return journey, takes goods B from shed 2 back to shed 1. Right, by switching platforms at the second shed. Okay. So the entire manoeuvre is a commutator. X, Y, X inverse, Y inverse. Okay, now I want you to think of this idea of switching platforms, right? You're a truck driver, and when you get to your destination and deliver the goods, you switch platforms in order to replicate the process in reverse, but moving other goods back to the first shed. So here's a cat falling, and cats are very adept. They land on their feet. And the reason for that is they've got very flexible spines and they exploit conservation of angular momentum. Okay, so the cat, for example, twists its spine, so the front of the cat, with its paws close to the axis of rotation, rotates clockwise, say 90 degrees. And the back feet, which are further away from the axis of rotation, cause a compensatory rotations, for argument's sake, 45 degrees anti-clockwise. Okay, that's X. Now, if the cat undoes X, it goes back to where it was, which is no progress. Okay, so it switches platforms. It shoves its front feet away from the axis of rotation and brings its back feet close to the axis of rotation. And then it undoes the twist of the spine, which we're referring to as X to the -1, and it achieves this effect of 45 degrees rotation, right? Because when it undoes X, the back feet being close, they will rotate, that part of the spine will rotate 90 degrees, whereas the front now will rotate anti-clockwise 45 degrees. And then it goes back to the original platform. I put the configuration of its arms and legs, and then it's completed the commutator and achieved a net rotation of 45 degrees. Okay, and it only has to, in this example, it only has to do that 4 times, and it will land on its feet. Now, of course, the cats are so flexible they can do it with one commutator, but I was just using those angles for the purposes of illustrating the technique. Okay, solving Rubik's Cube, I'll put up the diagram of the commutator and then do an illustration how it works. Here's a cube. There's only 2 things wrong with it. There's on the top face, there's 2 cubies that are out of orientation. Okay, so they've got the blue and the yellow, and I want to correct the orientation of the blue and the yellow. If I rotate it 180 degrees and then 90 degrees transversely, it will correct the orientation. But in order to avoid disrupting other parts of the cube, we'll do some obstacle avoidance. So before we rotate it, we'll just move some cubies out of the way and then rotate it 180 degrees and bring those other cubies back. And then we want to do the transverse rotation, so we'll do some obstacle avoidance for that. And then what we've done is we've corrected the orientation on the top for the yellow and the blue. That's X. It was actually 2 conjugates. Okay? If I undo that, I'll go back to where we were, which is no progress. So we'll switch platforms on the top layer. And now the yellow and red are in position to be transported back to the original shed. By undoing X, we'll correct the blue and the yellow. So we just have to, we do a transverse rotation first, and then 180-degree rotation second to undo what we did originally. And we've managed to land back in shed 1 with goods label B. The other thing is we're at the wrong platform, so we just switched back to our original platforms and we've landed on our feet. Okay. So that's how it works. So that's, I don't want to run out of time. I want to now talk about principles in combination. And to do that, I'll illustrate it with the Cayley-Hamilton theorem, which says that every square matrix M is a root of its characteristic polynomial chi of lambda. Okay, so this says chi of M is the 0 matrix, where chi of lambda is the determinant of lambda I minus M. Okay, so that's a very complicated polynomial in an indeterminate lambda. You substitute M for lambda and the density matrix for the number 1. You evaluate the matrix arithmetic and you get 0. And here's a famous 1-line proof of the Cayley-Hamilton theorem. Chi of M is the determinant of Mi minus M, is the determinant of M minus M, which is the determinant of the 0 matrix, which is 0. And of course, that's nonsense because the 0 at the end is a scalar. Chi of M is an M by N matrix. It's only a valid proof if N happens to equal 1, but the original manipulation is false, right? You have to take the determinant of lambda I minus M first, which is a complicated process involving determinants, and then you do the substitution. You don't do the substitution before the determinant expansion. The operations are far from commutative. Right? So that's a nonsense proof. Sorry? Yeah. So I'm sorry I can't hear anything. You have to. Any comments or questions? I can't hear. I'm really sorry. Proof for 3 by 3 matrices. Here's a proof. A very nice, elegant proof involving properties of the adjugate matrix and the telescoping sum. But it's the sort of proof Hannah Neumann would warn you against in an expository lecture or class, whatever. This could cause injury to a student, right? It could turn them off the mathematics. So rather than do this, something like this I will give as a reading exercise after students have been introduced to the theorem and got interested in it. And then they can see how they can modify the proof for n equals 3 to arbitrary n. So rather than prove it, let's explain it conceptually and try and illustrate connections. Okay, so first of all, we can conjugate a messy matrix M into something easier, D, right? And then it's a nice fact, conjugate matrices have the same characteristic polynomial. That's a plateau. The determinant of lambda I minus M equals the determinant of lambda I minus D. That's a nice exercise involving the multiplicative property of the determinant. Okay, so now we know M and D have the same characteristic polynomial. If we can show chi of D is a zero matrix, then chi of M must be the zero matrix, using the fact that polynomials of conjugates are conjugates of polynomials, using the same conjugating matrix. And that's a nice exercise, another sort of mini plateau. Okay, so it suffices to show chi of D is equal to 0. Okay, so then if D is diagonal, that's quite an easy demonstration. If D is a diagonal sum of Jordan blocks, that's rather nice, but it may not be appropriate. It depends, right? You know, it's a little bit technical introducing Jordan blocks. Of course, that relies on the Jordan canonical form theorem, which in turn relies on the fundamental theorem of algebra if you're working, say, over the field of complex numbers. And they're two really big plateaus. They're enormous theorems in the history and development of mathematics. We can take a sort of middle of the road approach. So suppose we can conjugate into something that's upper triangular, of which diagonal is a special case. That's something called a Schur decomposition, which is another plateau, significant plateau, not as heavy as the Jordan canonical form, but still significant result. Okay, so well, let's play around with upper triangular matrices, in which case the characteristic polynomial becomes a product of linear factors, each factor corresponding to a entry down the diagonal, which are the entries down the diagonal are the eigenvalues. Okay, so then you have an expression chi of D, which is very coherent, product of linear factors involving elements down the diagonal. So let's illustrate it when n equals 5 to get a feeling for what's going on. So here's our upper triangular matrix D. Here's chi of D. And can you see, each time you perform one of the linear factors, you're subtracting an eigenvalue from the diagonal. And that punches a hole in the respective position of the diagonal. It subtracts the eigenvalue from the other diagonal entries as well. But what you end up with is a succession of upper triangular matrices with these holes down the diagonal. Okay? And then you can see what happens. Okay, so if you multiply from right to left, those zeros down the diagonal cause an invasion of rows of zeros. And the invasion continues until you end up with a zero matrix. And it's so beautiful. You can do it from left to right. And now the zeros down the diagonal cause an invasion of columns of zeros. And you end up with the zero matrix. Now what's happening? Each time you perform a matrix multiplication, the rank of the matrix decreases by at least 1, possibly more than 1 each time. Okay? If you had a messy matrix M with numbers everywhere, you can't see the rank decrease, because it's all just a mess of numbers. With rows and columns of zeros, you can see the rank decrease down to zero, presenting, and you see the underlying duality relates to Hannah Neumann, trying to enthuse her students about the fact that the column and the row ranks of a matrix coincide. And that's, I've run out of time. And I've almost run out of time that I don't have to try and hear questions. So respectfully, if you would mind asking questions later, that will make it much easier for me, because I just will not be able to hear them here. Yeah. Okay, thank you very much.